Hello everyone, and welcome to today's Deep Dive Explainer. Today, we are going to trace the absolutely fascinating journey of a simple light ray. We're going to master the exact mechanics of how light bounces off surfaces, which we call reflection, and we'll unravel the mysteries of how it bends when passing through different materials, which is known as refraction. Okay, let's dive right into this, because by the time we finish up here, you are going to see the world around you in a completely different, highly illuminated way. All right, let's take a quick look at our roadmap for today. We're covering 1. Bouncing light and reflection basics. 2. Spherical mirrors and rules. 3. Unlocking the mirror formula. 4. Bending light through refraction. 5. Snell's law. And 6. Understanding spherical lenses.
Section 1. Bouncing light, reflection basics. Think about this morning when you were checking your reflection in the mirror before heading out. What is physically happening right there? Well, reflection is simply the phenomenon of light bouncing back into the same medium upon striking a polished surface. Imagine throwing a tennis ball straight against a solid brick wall. It hits the wall and it bounces right back at you, right? Light behaves in a very similar way. An incoming ray, what we in physics call the incident ray, hits a beautifully polished surface, like your bathroom mirror, and bounces right back as a reflected ray.
Now, I want to be clear, this bouncing isn't just some random event. It follows strict, predictable rules, which we call the laws of reflection. This brilliantly illustrates the predictable nature of physics. First, the incident ray, the normal, which is just an imaginary perpendicular line exactly at the point where the ray hits the surface, and the reflected ray, all lie in the exact same plane. Think of them as sitting perfectly flat on a single sheet of paper. Second, the angle of incidence, or I, is always equal to the angle of reflection, R. So the absolutely crucial takeaway here is that whether light is bouncing off a tiny pocket mirror or the massive flat surface of a calm lake, these universal laws hold perfectly true every single time. Section 2. Spherical mirrors and rules. Moving beyond flat mirrors, there is a stark contrast between our two types of curved spherical mirrors. On the left side of your screen, we have the concave mirror. The best way to remember this is to think of it as caving inwards, like a cave. When parallel light rays hit a concave mirror, they are forced to converge, or meet together, at one single focal point. Now on the right, we have the convex mirror, which bulges outwards. This specific shape forces the incoming light rays to diverge, or spread wide apart. And this exact diverging property is exactly why convex mirrors are used as rear-view mirrors on buses and cars, because spreading the light out gives you a much wider field of view to see the traffic behind you. Now, to figure out exactly what kind of image these spherical mirrors are going to create, we use 3 incredibly reliable rules for tracing light rays. Step 1. If a ray comes in parallel to the principal axis, it will always either pass through the focus or appear to diverge from it. Step 2 is literally just the reverse of that. If a ray passes through the focus on its way in, it bounces off perfectly parallel. And step 3, which is my favorite because it's so simple, if a ray is aimed directly at the center of curvature, it hits the mirror dead on and retraces its exact path straight backwards. Once you know these 3 rules, you can draw exactly where any image will form. Section 3. Unlocking the mirror formula. Okay, here is your golden key for calculations, the mirror formula. It states that 1 over f equals 1 over v plus 1 over u. Let's break those variables down cleanly so there's no confusion. U is simply the distance of your object from the mirror, v is the distance of the resulting image, and f is the focal length of the mirror itself. Right below that, we have the magnification formula, which tells us exactly how large or small the image will be compared to the real object. We find that by taking the height of the image and dividing it by the height of the object. Mathematically, that is completely equivalent to negative v divided by u. Now, I want to share a massive trick with you right here that is going to save you so many lost points on your exams. Object distance, u, is always negative. I repeat, always negative. Just take it as negative without any tension. This is entirely based on the Cartesian sign convention. Because we always, by standard rule, place the object on the left side of the mirror, the distance u is plotted on the negative x-axis. Remembering this one simple fact will save you from making countless frustrating sign errors in your math. Okay, so we've firmly established that light bounces beautifully off shiny, opaque surfaces. But let me pose a bit of a curveball question to you. What actually happens to our light ray when it hits something transparent? A window, a glass of water, or a thick glass slab? Section 4. Bending light. Refraction. This brings us to refraction. Refraction is officially defined as the bending of a ray of light when it passes from one transparent medium into another.
But why does it bend? Well, it's all about speed. Light travels at different speeds in different materials. It zips through empty space or the air around us incredibly fast, but when it hits a denser medium, like water or solid glass, it literally slows down. This sudden change in speed acts sort of like a car's wheels hitting mud on one side, forcing the light ray to pivot, bend, and alter its path.
Section 5. Snell's Law Explained. Snell's law is the ultimate mathematical constant behind this entire bending phenomenon. It tells us that for any two given media, let's say air and water, the ratio of the sine of the angle of incidence, I, to the sine of the angle of refraction, R, will always equal a constant number. We call this specific constant the refractive index. It's essentially a standard measure of just how much a particular material is going to resist and bend that light ray. Understanding the exact direction of that bend is super vital. Let's look at the two scenarios. When light travels from what we call a rarer medium, like air, where it moves freely and quickly, into a denser medium, like glass, where it has to slow down, it bends towards the normal line. But flip that around. When it escapes from that dense glass and breaks back out into the rare air, it speeds back up and bends away from the normal.
Let's see how this all builds together when we look at a classic textbook example: refraction through a rectangular glass slab. When a ray first hits the glass, it slows down and bends towards the normal. Then it travels straight through the glass until it hits the other side. As it exits back into the air, it speeds up and bends away from the normal. Because the glass slab has perfectly parallel sides, that first bend inward is completely canceled out by the second bend outward. The fascinating result? The emergent ray, the one coming out at the end, is perfectly parallel to the original incident ray that went in. It's just been physically shifted over a little bit.
Section 6. Understanding spherical lenses. Now, let's transition to our final concept and see how we combine curved surfaces with refraction to create functional lenses. Notice how lenses work as the exact opposites to the mirrors we studied earlier. Here on the left, a convex lens is thick in the middle and thin at the edges. When light passes through, the lens bends it inward, converging the refracted rays to a neat focal point. But on the right, the concave lens is thin in the middle and thick at the edges. This specific shape causes the refracted light rays to scatter and diverge outwards. Real quick, before we wrap this up, I have to give you a vital piece of trivia that doubles as a secret weapon against trick questions. I call it the no-bending rule. We've talked all about how light bends when changing mediums, but there is one major exception. If a ray of light hits a boundary exactly perpendicular, what we officially call normal incidence, it passes straight through with absolutely zero bending. None. It will change speed, yes, but its path remains perfectly rigidly straight. Do not let those tricky exam questions catch you off guard on that one. And that brings us to the end of our journey today. From the predictable bouncing of reflection to the fascinating bending of refraction, you've just unlocked the hidden geometry of light. So I want to leave you with this final provocative thought. Knowing that you can now predict the exact mathematical path of light, how does that change the way you look at the spectacles sitting on your face, or the magnifying glass in your drawer, or the incredibly complex camera lens built right into your phone? It's not just magic, it's physics. It's happening all around you, all the time, right in front of your eyes. Thank you so much for joining me on this explainer. Keep observing the world, and I'll catch you all in the next one.